Okay. So I hope all of you have got this study pack, States of Matter study pack 4, printed. Right. So I'll be discussing about the states of matter different to the 3 states of matter and the calculations based on the gas laws, the universal gas equation. In fact, matter is anything which occupies space and has a mass. The 3 states of matter is solid, liquid, and gas. As you know, if you analyze the particles, how they organize in these 3 states, the solids, the particles are in fixed positions. These particles can be atoms or molecules, and they are unable to move. They can only vibrate on a given axis. And the solids have a definite shape, right? And you cannot compress the solids, right? Because you can see between these particles, and there is no space between the particles. So definite shape and volume, particles are very closely packed. There's no space in between. You cannot compress, and then these particles cannot freely move. They can only vibrate on a given axis. They cannot freely move. As the liquids, particles are quite fairly far apart compared to the solids, right? And these particles, in fact, cannot be compressed again. The liquid cannot be compressed, but it doesn't have a definite shape. In fact, it takes the shape of the container in which it is filled. And you can very slightly compress the liquids, but to insignificant amount compared to gases. And the particles can freely move. Particles in a liquid can freely move. As for the gases, it doesn't have a definite shape at all or a volume. Particles you can notice they're much far apart. They can freely move and can be easily compressed. Particles can be, the gases can be easily compressed because there's huge space between the particles. And these particles are arranged not in a regular manner, irregular manner, and they are free to move throughout. And these are the 3 states of matter and how they are interchanged. Please copy this. Copy the arrangement of particles in the 3 states. Right, so these particles, let's see how these 3 states of matter can interchange. For a solid, if you supply heat, what happens, the particles vibrate. They cannot freely move, but the particles vibrate because they take in heat energy and they start vibrating, right? And they convert the heat energy into kinetic energy. So at one point, when they keep vibrating, they overcome the intermolecular attractions with the other solid particles, and that's the point where we say this point where the solid begins to melt, right? That's called the melting point of the solid, and that's the temperature where solid begins to melt. That's called melting. That's the change of state from the solid to liquid, right? That happens when the temperature is increased. So the temperature at which the solid begins to melt is known as the melting point. Now, once the solid is melted, it turns to liquid. What happens? You keep increasing temperature. You keep increasing temperature. What happens? The particles, they gain in heat energy and the kinetic energy increase. As a result, they vibrate and move very fast. And the particles which are on the surface of the liquid, they lose their interactions with the other particles and they move on to the gaseous state. So that's the change of state, which is known as evaporation. That is from the liquid changing into the gas, liquid to gas. Say, for example, say you are heating a vessel of water in a closed system, right? So when you heat, what happens? The liquid particles gain in a lot of kinetic energy and they start vibrating and moving faster. And the particles which are on the surface of the liquids, they lose their interactions with the other liquid particles and they jump off to the gaseous state. And this is known as evaporation. At one point, what happens when the gaseous molecules increase a lot, these gaseous molecules will bombard on the wall of the container as well as on the surface of the liquid. These gaseous molecules will bombard on the wall of the container as well as the surface of the liquid. So when they bombard on the wall and the surface of the liquid, they exert a certain amount of pressure. That is what we call as the vapor pressure. That is the maximum pressure exerted by these gaseous molecules on the wall of the container. Now, what happens if you cool the system? These gaseous molecules, they have very high kinetic energy. As a result, they vibrate and move faster, exerting a lot of vapor pressure. When you cool them down, what happens is that they lose their kinetic energy. So when they lose their kinetic energy, they reform their strong intermolecular attractions. When the strong intermolecular attractions are reformed, that is a point we say the gas turns into liquid. Right? This is condensation, the change of state where the gas turns to liquid. And this is exactly what happens in a condenser. The Liebig condenser, where you have if I'm to draw the Liebig condenser, you have an inner tube and you got the outer tube, and cold water travels in the outer tube against gravity, right? This is water in and this is water out. Right? Why against gravity? Because if not, the outer tube will not get cooled. The inner tube will not get cooled. So gases travel this way, and what comes out is a liquid. Enters is gas, comes out is liquid. So the water which is sent against gravity will ensure that the inner tube is cool. So usually when you draw the condenser, if it is condenser which is used for the distillation process, it should be slanted like this, right? Then the liquid comes out and the water is sent always against gravity from bottom to top. That ensures the proper cooling of the inner tube, right? So you send the gases, what comes out is a liquid. So exactly the same process happens in the condenser, right? So that's called the condensation. And this liquid, if you further decrease the temperature, this liquid, if you further cool, decrease the temperature, it solidifies, right? It loses its kinetic. Molecules will lose the kinetic energy and they reform their strong intermolecular attractions, and then the liquid turns into a solid. This is known as the freezing, and the change of the temperature at which this happens is known as the freezing point. Now, there are certain solids which has very strong interactions between the other molecules. Those solids which has a strong interaction with the other molecules, like for example iodine, or even that is iodine is a molecular substance, and if you take diamond, graphite, it has very strong interactions between the atoms, very strong ionic the covalent bonds in diamond graphite. So in such molecule, what happens is that when you increase the temperature, the solid is directly turns into a gas without going through the liquid state, right? Solid directly turns into a gas without going through the liquid state, because the reason is that the intermolecular attractions are so strong you need to supply a huge amount of energy, and you supply that huge amount of energy. What happens, without going to the liquid state directly, it transforms from the solid to the gas. Now, this type of change of state where a solid turns to a gas in a direct single step is known as sublimation. And likewise, such gaseous molecules which has very high kinetic energy, if you decrease the temperature, they reform their strong intermolecular attractions and move on to the solid state, gas to solid directly, or solid to gas directly. So both ways is referred to as sublimation, change of state from solid to gas and gas to solid. Am I clear to everyone? Right. So let's see about what is boiling. Now, the boiling occurs when you try to heat a liquid, and then liquid evaporates. You can see at one point, you see the solid, the liquid, tiny bubbles appearing in the liquid. And further, when you keep increasing the temperature, what happens, the bubbles will spread throughout the liquid. And at that point, if you check the temperature, there won't be any further rise in temperature, right? So that is the point where we say the liquid boils, right? Boils, that is, you see tiny bubbles appear in the actual liquid. So when you keep increasing temperature, there will be a point where there is no further rise in temperature. For example, if you take water at around 75 or 80 degrees Celsius, you see tiny bubbles appearing. So that's the point where we say water begins to boil, but that's never the boiling point of water. And when you keep increasing temperature at one point, you see the temperature remains constant and bubbles spread all over the liquid. That's the point where we say the boiling point. When a solution reaches boiling point, further increase in temperature will not cause any heat rise or temperature rise in the actual liquid. Any pure substance will have a unique boiling point as well as a freezing point. So therefore, we can use the boiling point and freezing point as a method or indication to check whether the compound is a pure or impure compound, right? You can now try the next question. Write the names given for this change of state. So the change of state of A, which is solid to gas or gas to solid, that direct change of state is known as sublimation. And B, solid to liquid, is melting. And then C, which is liquid to solid, is freezing. And D, liquid to gas, is evaporation. And E is gas to liquid, is condensation. Right. So let's see about the next, what are ideal and real gases. Now, there's nothing, in fact, the real gases are the gases which you really actually come across, right? All the gases which you come across, they all are real gases, which means there are intermolecular forces. There is a mass for real gas, there's a size, and real gases does not obey the assumptions of the kinetic theory. I'll be explaining what is kinetic theory shortly, right? All the gases we encounter, real life is all real gases. As for the ideal gas, there's nothing called ideal gas, but it's just a concept. Just a concept. The ideal gases, they do they do obey all the assumptions of the kinetic theory. In fact, the no gas. In fact, there is no gas which is ideal in reality, but it's just a concept. Now, you might wonder, if there's no gas, ideal, why we study about ideal gases. In fact, that's a concept, and that obeys that means ideal gases obey the assumption of the kinetic theory. And there are certain conditions where the real gases will come close to ideal behavior. At certain conditions where real gases behave like ideal gases. Now, what is ideal gas, and what are the characteristics of ideal gas? Now, real gases, there are intermolecular attractions, right? Real gases, there are intermolecular attractions. But the thing is, in ideal gas, there is no such thing, right? Impossible, right? Because we know any gas should have intermolecular attractions. Any gas should have intermolecular attractions, because we have studied intermolecular attractions under chemical bonding. Anything which has electrons should have intermolecular attractions, because any compound or any molecule which has electrons, dispersion London forces, remember? So this is impossible, like, to have ideal gas, which is gas without intermolecular attractions. And then another characteristic of ideal gas is that ideal gases have a mass just like a real gas, but the thing is, there's no size, meaning it doesn't occupy space at all. Then again, this is something hard to imagine. It has a mass, but it doesn't occupy any space in a container, right? Meaning the size is negligible. And the ideal gases, they obey all the assumptions of the kinetic theory. So there's something called ideal gas, but the real gases under certain conditions come close to ideal behavior. We'll study shortly what are those conditions. So therefore, we just ideal gas is just a definition, just a concept, just an idea, right? There's nothing called ideal gas. If you ask me examples for ideal gas, none. There's no examples for ideal gas, right? It's just a concept. But the real gases under certain conditions can come close to ideal behavior, right? For example, at high temperature. Now see, if the temperature is very high, the particles will gain in extra heat energy, and they start vibrating and moving faster. So when the temperature is very high, the vibration between the molecules, gaseous molecules, will be very high. Vibration is very fast, right? When the high temperature is very high. So when the vibrations are very fast due to the high kinetic energy, it will be as if it will have like no intermolecular attractions, because vibrations are very fast, and then it will be extremely like have no intermolecular attractions. So under very high temperature, the real gases will come close to ideal. It is not 100% ideal, but it will come close to ideal behavior. It will come close to ideal behavior because intermolecular attractions will lose when the temperature is very high. Right? And also, so that's one condition where the real gases come close to ideal behavior, and at very low pressure. Now we know the pressure can be decreased when the volume is increased. So this is the container, and